When you look at Edward Tufte's The Visual Display of Quantitative Information or any of his other books, you can legitimately ask the question whether or not it's possible to recreate these kinds of figures with modern plotting tools. Here I'm showing the work by Anisha Zaveri. There are other examples out there. This was published on a website some time ago, and I just copied the solutions over into a notebook environment so we can play with it. The goal is to recreate this figure. This is an image from Tufte's book. You can see that the axis spines are missing. The lines are not connected to dots. There is text in an unconventional position, and we are showing some kind of variance over part of the time series here. The data set is per capita budget expenditures in constant dollars. So this is inflation corrected from 1967 to 1977, ranging from $300 to $400 here on the y-axis. Look at the code. We import a few things. We import matplotlib pyplot as PLT. This is a standard way to import the pyplot package. And we use a few other elements from matplotlib here, ticker and patches, and we'll see below how we deal with this. First, we are defining the data. On the x-axis, we have a list that ranges from 1967 to 1978, and the y-axis are the values that we see on the plot. We're making a canvas. We define a figure size using the subplots function in pyplot. We get the figure back and the axis in the variable fig and x. To remove the spines, we can ask the axis to give us the spine keys, and then we iterate over the spines, which in this case are only 2, and set the visibility to false. This makes away with the x and y axes. Now we can set our axis limits with the function set ylim between 290 and 420 to get our y-axis limits, and the same for the x-axis by setting xlim from 1966.5 to 1979 to give us some space. For the x-axis, we want a tick mark at each year. For the y-axis, we want our tick marks to be within the range 300 to 420 in step sizes of 20. To create the spacing that we can see here between the tick marks and the values, we can increase the padding here to 8 for the y-axis and the x-axis. We then create a formatter for the text by our tick marks using the func formatter and giving it the argument format ticks. Format ticks is a function that takes in the text and the position and returns a formatted string that has the dollar value added for the y-axis. So this creates the dollar sign before the y-axis values without us having to add this manually to every element. Now we set that formatter for the y-axis. We can say set major formatter, take the return value from func formatter and stick it in here to ensure that our y tick marks are formatted with a dollar sign. Here comes a trick. We're now plotting our data twice. We're using a scatter plot for our x vector, which is the years, and the y vector, which is the dollar amounts. We set our size to 64 and the color to white and the z order low. On top of that, with a higher z order, we plot at the same locations markers that are smaller in size in black. Then we are adding connecting lines here, using again the same data. We're coloring them black. Our z order is the lowest here. This is below the white and the black that is being plotted, and we give the lines some width. We're plotting the lines in black, which will be all connected. We're plotting white circles on top of this, and then the smaller black circles in the middle of the larger white circles, creating the illusion of disconnected line segments here. The next two lines add the two horizontal dotted lines that you can decipher here. This gives us these elements. Lastly, we add some text, the per capita budget expenditures in dollars, and the 5%. We also add a bar. Lastly, we're plotting the plot. If you want to see what you've created, you need to always call plt.show. We're executing this. You can see at the bottom now that we are having, this is the bar that we just drew. We're having the exact information displayed in exactly the way that Tufte did it in his plot, perhaps slightly different aspect ratio in the horizontal and vertical, and a different font because my system does not have the original font used here. But if I switch back and forth, you will hopefully agree that the overall character of that plot has been captured, and if we find a similar plot, we can perhaps employ this. Another example shows the traffic deaths per 100,000 in Connecticut, Massachusetts, Rhode Island, New York from 51 to 59. You can see again, we have 51 to 59 at the bottom. We have disconnected spines and these lines that are differently hatched to ensure we understand what they are representing. There are elements that are repeated from above and others that are new. I will not go over all of the details. You can see that the code isn't very long. And if we execute this, we can again see that this plot is being regenerated in a way that is very similar to the line plot that Tufte originally created. I think the important lesson here is that you can simulate certain aspects, like the white space around the data points, by creatively layering. Don't think about how to draw shorter lines. Just put connected lines on the bottom and draw something that is white on top, which will always give you a consistent spacing around your actual data point, which is smaller. For some pieces, you will have to write some specialized code, like this line segment here for Connecticut, and you can see that there's something special that is happening here. But again, there's just one line element being plotted on top of what is already being created. So instead of thinking hard, how can I create so many line elements that are thin, and then one that is thicker, and then everything else that is thin again, just draw a thin, continuous line, and then deal with the special cases separately. I hope that convinces you that matplotlib has the power to create highly customized plots if you understand the library and put in the effort that is necessary to convey the story that your data tell in the most appropriate way.